What's up, my pre-calc people? I'm Michael Princhek, and in this video, we're going to tackle 25 problems that are going to help you review for Unit 2 of AP Precalculus over exponential and logarithmic functions. Now, please understand that these 25 questions aren't everything from the entire unit. By no means can you watch this video, know these 25 questions, and expect to ace your test in class. These are just 25 really good questions that should help prepare you for the types of questions that you just may see on your Unit 2 test. Now, if you're looking for more practice, please check out my ultimate review packet for AP Precalculus. There's a free trial of it right now, and in that packet, you have access to study guides over every single topic of AP Precalculus, and those study guides are filled with way more than 25 practice questions. And you also get full answer keys to all those study guides. There's additional practice-free response questions. There's 2 full practice exams to prepare you for the AP exam in May. Basically everything you need, not just to make sure that you're ready for unit and quizzes in class, but that way you're ready for that AP exam in May as well. All right, let's dive into these 25 questions right now. And here's question number 1. It says, consider an arithmetic sequence with terms a sub 3, the third term is 3, and a sub 10, the 10th term is 24. Find a formula for the sequence. Now here is a formula for any term of an arithmetic sequence. Now, pretty simple formula, and let me explain. First, we have k and a sub k. That is the input and the output, any term and its term value. And I actually know 2 terms, so I can actually put a 3 for k and a 3 for a sub k, or I could put a 10 for k and a 24 for a sub k. But what I don't know is the common difference. I need to figure out what that common difference is. It's actually really easy to figure out. First, I'm going to say the third term. The third term is 3. There it is. And if I want to get to the 10th term of 24, I have to think, how do I go from the third term to the 10th term? Well, I would need to add 7 differences. So 3 is the third term, and I would need to add on 7 differences to get to the 10th term. That should hopefully make a lot of sense. 10 minus 3 is 7. So now I just created a really simple equation I could solve. All I got to do is subtract 3 from both sides, and I get 21. Divide both sides by 7, and I get 3. So my common difference is 3. Now I'm just going to go back to my formula, and I could use any term I want. So I'm going to use this term right here. So 24 is the value of the 10th term. So 3 is going to go in for D, and 10 is going to go in for K because the 10th term is 24. I could have also put a 3 and a 3, just so you know as well, because I know the third term is also 3. And then again, the common difference I know is 3 as well. Now, the other thing I'm going to do real quick, and you don't have to do this, but it does help, is to just quickly distribute this, and I get 24 plus 3n minus 30. I can combine my like terms there, and I get 3n. 24 minus 30 is negative 6. Now, interesting enough, I want to show you a second way you could solve this problem that I kind of prefer, but it's completely up to you. The other way we could think of this is as long as we know that arithmetic sequence is a linear function. So all linear functions have this form, a plus bx. So what I could do is I could take these 2 pieces of information, I could create 2 equations. So the first says, if I plug in 3, I get 3. The second is if I plug in 10, I get 24. Okay, so I basically created 2 equations, and now I could use substitution to solve. So I'm going to solve this first equation for A. I'm simply going to subtract the 3b over. So I get 3 minus 3b equals A. I'm now going to plug that A right in here. So I get 3 minus 3b plus 10b equals 24. And combining like terms, the negative 3b and the 10b make positive 7b equals 24. Subtract the 3, 7b equals 21. Divide by 7, and b equals 3. Now I'm going to take that b, plug it back into here to solve for a. So a equals 3 minus 3 times 3. That's 3 minus 9, which is negative 6. So now when I go back to my original equation, I'm going to substitute in a, negative 6, plus 3 for b, and I have my linear equation, which just so happens to be the arithmetic equation as well. And you'll notice there's no difference other than just using x instead of n. So 2 different ways to solve that one. All right, question 2 is very similar, but this time we're given a geometric sequence, and here are 2 terms. The second term is 20, and the 5th term is 160. Now, I got to remember the formula for a geometric sequence looks like this. g sub k, that's the value of the kth term, times r, my common ratio, it's what I'm multiplying by, raised to the n minus k. And just like with arithmetic, k and g sub k is any term I want. So again, I could plug in a 2 for k and a 20 for g sub k, or a 5 for k and 160 for g sub k, because I know two terms. What I don't know is my common ratio. So here's how I'm going to find it. The 20th term, or excuse me, 20 is the value of the second term. And if I want to get from that second term to the fifth term of 160, I'm going to need to multiply by 3 ratios. Remember, geometric sequences, we multiply. So if I'm at the second term of 20, I'm going to multiply by r, multiply by r, multiply by r, so r times r times r, or r to the third, and that'll get me to the fifth term. Multiply by r gets me to the third term, multiply by r again gets me to the fourth term, multiply by r a third time, and I get to the fifth term. So that's why this equation makes sense. Then all of a sudden I just have to divide both sides by 20. R cubed equals 8. Raise each side to the 1/3 power to get rid of that 3, or use a cube root, and r equals 2. Now I'm going to go back to my formula, and remember, I have two different points, two different terms that I could use. Doesn't matter which one you use. I'm going to use the second one right here. So 20 is the value of the second term. 2 is my common ratio. And I'm going to do n minus 2, again, because 2, the second term, was 20. Again, that comes from right here. Now, this is a great final answer. There's nothing wrong with this final answer, but I do want to put it into my exponential formula, right? Just because it's very common to do this. You don't have to do this, but I want to make sure you show you how to do this because it'll be very useful. Geometric sequences are exponential functions, and exponential functions come in the form a times b to the x. So if I want to get it into that form where I have a times b raised to a single power of just x, well, what I have to do is break this apart a little bit. So I have 2 raised to the n minus 2. So that's going to be 2 raised to the n, and then 2 raised to negative 2. I'm just using my exponent rule in reverse there. And then I'm going to go ahead and say, well, wait a minute. 2 raised to negative 2, that's 1/4. So I get g sub n equals 20 times 1/4 times 2 raised to the n, and 20 times 1/4 is, of course, 5. So I get 5 times 2 raised to the n. Now, again, this is no different, right? Like, I didn't have to do that. This is a great answer right here, but this is just putting it into that exponential form. Now, if you want me to show you another option here, another way you could do this one, you could also go back and say, okay, listen, I know geometric is exponential, and exponential is y equals a times b to the x. And what I can do is I can create two equations. When I plug in 2, I get 20. And when I plug in 5, I get 160. So I created two equations with my 2 points, or my 2 terms. Now I'm going to solve this first one for a by simply taking the b squared and dividing it over. Then I'm going to take that a and I'm going to substitute it in right here. So I get 20 over b squared times b to the 5th equals 160. These b's are going to reduce. B to the 5th over b squared is b to the 3rd. So I get 20 times b to the 3rd equals 160. Divide both sides by 20. I get b to the 3rd equals 8. Take a cube root, or raise each side to the 1/3 power, and I get b equals 2. I'm now going to take that 2, plug it all the way back over to here to help me find a. A equals 20 over 2 squared, which is 4, and 20 over 4 is 5. So I get y equals 5 times 2 raised to the x, which is what I got over here as well when I did that reducing. So 2 different ways to do this one. I know I want to take some time there to show those, but I think it's really important that you understand those 2 different ways to solve those arithmetic or geometric sequences. All right, moving into the third question. Here we have a function, and we're asked several different questions about the function and behavior. But we're also asked, is it decreasing, increasing, and what about the rate of change? So let's first process what you need to know. You need to know without a calculator what this graph looks like. Now, because my b value is less than 1, but still greater than 0, your base always has to be greater than 0, meaning your base cannot be negative for an exponential function. Well, that tells me instantly that I have a decay function, right? So I have a decay function that's going to look like this, okay? Terrible drawing, but you get the idea. Again, very bad drawing. Maybe I could try to make it a little bit better here for you. But again, the point is you need to have a basic understanding of what this graph looks like as a decay function. Now, there's no other transformations. There's no negatives. There's no reflection, anything like that. So now I'm good to go. So what is the end behavior? Well, the limit as x approaches positive infinity for this function is 0. We see that the right-hand side is going to get closer and closer to 0. What about the end behavior of x decreases? Well, the limit as x goes towards negative infinity, that's the left-hand side of the graph, is going towards infinity. We see that the left-hand side is going all the way up towards infinity. All right, is the function decreasing or increasing? We can clearly see from left to right the function is decreasing. And what about the rate of change? Well, the graph is concave up, so the rate of change is increasing. So this graph is decreasing at an increasing rate. The rates of change are all negative because it's decreasing, but they're becoming less and less negative, which means that the rate of change is actually going up because it's becoming less and less negative. All right, here's another one. This time we see that our b value is greater than 1. When your b value is greater than 1, you have exponential growth. Okay, that's awesome, but wait a minute. We have a reflection across the x-axis. So because that negative out in front, we're going to actually be reflected across the x-axis, and there is our graph right there in blue. So what is the end behavior as x increases without bound? Well, let's find the limit as x goes towards infinity. And if you look at the right-hand side of the graph, it's going towards negative infinity. What about the limit as x goes towards negative infinity for our function? If we look at the left-hand side of the graph, we see that it's going towards 0. All right, is the function increasing or decreasing? Well, from left to right, we clearly see that the function is going down, so we are decreasing. But the rate of change, well, it's concave down, so the rate of change is decreasing. The rate of change is becoming more and more negative, which means the rate of change is going down. It's becoming more and more negative, right? It's decreasing, and we see that through the graph being concave down. So the graph is decreasing at a decreasing rate. All right, here is another one. This time we see a b value that's once again greater than 0 but less than 1. So that is an exponential decay. There's a decay. But wait a minute. We have a reflection across the x-axis. That's actually going to turn our decay into a growth. If we reflect that blue function, the decay, exponential decay, it's going to reflect across the y-axis and now become exponential growth. So looking at that red graph, what's happening? Well, the limit as x goes towards infinity for our function is infinity. We see that the right-hand side is going up. And again, notice it's a really terrible drawing, but it's all you need to get a basic understanding of what's happening here. And the limit as x goes towards negative infinity for this function, this is our left end behavior, is going towards 0. All right, is the function increasing or decreasing? Well, it's clearly increasing. If we look from left to right, it's going up. And it's also concave up, so its rate of change is increasing. So it's increasing at an increasing rate. The rates of change are becoming more and more positive, so they're increasing, hence why that red graph is concave up. So it can be a little bit tricky there. As long as you understand the different transformations, you can make a quick graph and really kind of get a feel for all of these different features. All right, what about some log graphs? Well, before I get too far here, let's quickly remind you what a basic log graph looks like. A basic log graph has a vertical asymptote at x equals 0, and then it looks like this. It's the inverse of an exponential function. So that's what a basic log graph looks like. But wait a minute, because we have a negative out in front, that is a reflection across the x-axis. So let's draw what that would look like. So if I take that blue graph right there and I reflect it across the x-axis, it's now going to do that. So kind of a weird looking graph. That's exactly what it's going to be doing. So you need to know the basic log looking graph, and then we need to know what that negative out in front does. All right, so what is our limit as x increases without bounds? So the limit as x goes towards the right, towards positive infinity. Well, we see that the right-hand side of the graph is going down towards negative infinity. All right, what about as x decreases without bound? Well, that's actually very interesting. Because of that vertical asymptote, x actually cannot decrease without bound. X actually is bounded, right? X approaches 0 from the right-hand side. So we're not allowed to go all the way towards infinity because that vertical asymptote, our log graph gets like trapped, right? It can't go past that vertical asymptote. So it's going to make a choice. It's going to go straight up or straight down. But because of the reflection, the left-hand side, as x approaches 0 from the right, is going towards positive infinity. Hopefully that made sense. All right, describe if the function is increasing or decreasing. Well, the graph is clearly decreasing from left to right. And what about the rate of change? Well, it's concave up, which means that the rate of change is increasing. concave up. The rate of changes are negative throughout this graph, but they're less and less negative, which is why technically the rates of change are increasing because they're becoming less and less negative. That's a tricky one, so make sure you really take your time with that. All right, let's do another one here. So once again, we have a basic log graph. So I see logs, so I think, okay, what's a basic log graph look like? So just really basic, we got that vertical asymptote at x equals 0, and then we increase from there. All right, that's awesome. There's no reflections here, so don't have to worry about any reflections, but there is a horizontal translation left 4. So that's actually going to take that vertical asymptote and it's going to move it left 4. So that vertical asymptote is now over here at -4, and then the graph is going to go like that. So really rough picture again, but again, the idea is because of that translation left 4, we now have that vertical asymptote at -4. So what is the end behavior as x increases without bound as we go to the right of the function? Well, look at that right-hand side. It's going towards infinity. And what about the limit as x decreases without bound? Well, first, we're not allowed to decrease without bound because the actual x's get trapped by that vertical asymptote. So x actually goes towards -4 from the right. And as we go towards -4 from the right, our graph is going towards -infinity. All right, is the graph increasing or decreasing? Well, it's clearly increasing. If we look at the graph, we see that it's going up, and it's doing so at a decreasing rate because it's concave down. The rate of change is becoming less and less positive, which means the rate of change is going down, and that's why we are concave down and our rate of change is decreasing. So when it comes to the graphs of exponential and log functions, you got to be able to make a rough, quick sketch based on the different transformations and the basic graph that we know, and then you should be able to make these decisions pretty easily. All right, question number 8 says, is this function represented in this table exponential or logarithmic? Well, remember, exponential, the outputs change proportionally. The outputs change multiplicatively. They multiply. The inputs change at an additive rate. And then logarithmic, it just is the inverse of that. The inputs change multiplicatively or they change proportionally. The outputs change additively. So if we look at this graph, we're going to say this one's definitely, or not this graph, but this table, this one's definitely logarithmic. The inputs, x, are changing multiplicatively, right? They're multiplying by 2, multiplying by 2, multiplying by 2, and the outputs are adding to. So when we see that happen, that's logarithmic. In this graph here for question number 9, or this table, I keep saying graph, sorry, for this table, we see the opposite. So this is exponential. We see that the inputs are changing additively, up 1, and the outputs are changing proportionally or multiplicatively. They are multiplying by 1/2. So that is going to be an exponential function. All right, let's do some compositions now here. Hopefully these aren't too bad. So we have two functions, g and f. They're both linear functions, and we're asked to find f composed of g composed of 2. So we're simply going to start on the inside here. We're going to plug 2 into g. So I get 2 times 2 minus 1. That's obviously going to be 3. That's pretty simple. Then we're going to take that value of 3, that output, and we're now going to use it as my input into f. So we have 6 minus 7 times 3. That's 6 minus 21, which is negative 15. So pretty easy to do there, nothing too difficult. All right, we're going to do a very similar problem, same two original functions here, g and f, but this time we're going to keep it analytic, right? We don't have any value, we're just going to leave it as x. So we first have to do is plug x into f. Well, that's really easy to do. That's just 6 minus 7x. But now we're going to take that f of x, 6 minus 7x, and we're going to plug it into g. So we have 2 times 6 minus 7x minus 1. So I literally took f, 6 minus 7x, and I plugged it into g, so it became 2 times 6 minus 7x minus 1. Now I'm just going to do a little bit of multiplication to clean this up. I get 12 minus 14x minus 1. 16 minus 1 is 15, so I get, oh my gosh, I did my math wrong there. I'm so sorry. Terrible math real quick. At least I caught my mistake, right? 2 times 6 is 12, not 15. So 12 minus 1 is 11, so I get 11 minus 14x as my final answer for g of f of x. All right, here's another one. Again, same two original functions, but check out this one. It's a pretty good problem because this combines inverses with compositions. So it wants me to take f of 3 and plug it into the inverse of g. So first, let's figure out what f of 3 is, because that's pretty easy. So we have 6 minus 7 times 3. That's 6 minus 21, or negative 15. But now what I have to do is I have to plug negative 15 into the inverse of g. So very quickly, I have to figure out what the inverse of g is because I can't do it until I figure that out first. So what is the inverse of g? Well, I'm going to take g, y equals 2x minus 1. I'm going to switch my x's and my y's. And I'm going to solve for y. So I'm going to x plus 1 equals 2y, and then divide by 2. So x plus 1 divided by 2 equals y. So the inverse of g is x plus 1 divided by 2. So now I'm going to take negative 15. I'm going to plug it into that inverse. So I get negative 15 plus 1 divided by 2. Negative 15 plus 1 is negative 14 divided by 2 is negative 7. So pretty cool problem there where we're combining compositions with an inverse function. All right, question 13. Let's move into some log problems here. So we want us to evaluate this log expression. Now there's no equal sign here, so I'm not solving anything. There's no x's, so I'm simply trying to figure out what this is. Now, this is going to be a non-calculator problem, so we need to be able to know some basic logs without using a calculator. So first, let's talk about log base 2 of 8. This is saying 2 raised to what equals 8. Remember, logs are exponents. So 2 raised to what equals 8. You guys should know that. That's not too difficult of one to know. That's going to be 3. This next one right here, log base 5 of 25, is going to say, hey, 5 raised to what equals 25. Again, logs equal exponents. So I'm thinking 5 raised to what equals 25? Oh, 2. That's easy. So I have 3 plus 2, final answer 5. Really, really simple there. Now be careful. I'll get kids on these problems that try to use our log properties, but I can't because I have 2 different bases. You can only use those log properties if you have the same base. All right, here's another one, very similar in nature. So again, no x's, no equal signs, no solving. I'm just trying to figure out what each of these values are. And if I'm going to give this to you on a non-calculator problem, you should be able to figure it out. They should be very, very doable. So I'm thinking, okay, 49 raised to what equals 7? Well, I know the square root of 49 is 7. Oh, a square root is a 1/2 power. So there we go, pretty easy. Now this next one's a little bit tougher, but I'm thinking 2 raised to what equals 1/16. Now I got to be careful here because when you create a fraction, it's because of a negative exponent. So I must have been a negative exponent, which moved me to the denominator, and I know 2 to the 4th is 16, so the answer there is negative 4. 2 to the negative 4 is going to go in the denominator as 2 to the positive 4, and that's where I get the 1/16. So you got to be able to know those negative exponent rules as well. Now be careful here because we got to take 1/2 minus negative 4, which is actually could have turned into 1/2 plus 4, or 4.5, or 9/2 if you'd rather a fraction. So again, just knowing some basic idea of what logs are and how we can evaluate some pretty basic log expressions is going to be very, very useful. Let's do one more here. This one's with natural logs. Now remember, a natural log has a base e. So for this first expression right here, we're doing e raised to what equals e? Well, of course, that's 1. When my base is e, we don't write it there, but there really is a base of e there. So e raised to what equals e, and that question mark is the answer to my natural log, and of course that's 1. For this next one here, I have e raised to what equals e to the 3rd, and that's actually pretty easy. That's going to be 3, right? E raised to the 3rd equals e raised to the 3rd. So 1 plus 3 equals 4. Now real quick here, because I do have the same base, on these I actually can use my log properties. They both are base e, so I could bring addition together with multiplication. So it would look something like that. Right, the addition of 2 blocks, the same base, comes together with multiplication on the inside, and that's going to be natural log of e to the 4th. I could then use another log property where that 4 comes down in front of the log, and the natural log of e is 1, so I just get 4 times 1, which is 4. Another way that you could get 4 here. Anytime your base of your log and what you're taking the log of are the same, they undo each other and you just get 1. So that is why natural log of e is 1. All right, so in this problem here, back to another inverse problem. So we have a table of values for a function f. We're asked to find the inverse of the function when f is -6. So I'm going to plug -6 into the inverse. So how do you find the inverse of a table? It's so incredibly simple. All you do is switch all of your inputs and your outputs. So 3, 1/3, -1, and -6 are now my inputs. And the inverse function, or the outputs, are the old inputs. So that's -2, 0, 1/3, and 3. So now it's really easy to just look right here. When I take -6 and I plug it into my inverse, I get 3. So there's my final answer of 3. So really, really simple to deal with inverses when you have a table. All right, so here is a question. This is I'm going to do several different questions based on this graph, but here we have some type of piecewise function where we have this graph made up of these 3 linear pieces. All right, so this is a graph of f of x, and we're going to allow h of x to be the inverse of f. So just keep in mind that h of x is the inverse of f. Now, how do you find the inverse of a graph? Well, you literally just take the points, switch your x's and y's, and you have your new points. And then you play connected dots. Pretty simple. But I want to teach you why we don't necessarily have to do that for this question. Now, the first one says, what is the domain of f of x? Well, f of x is what I'm looking at in the graph, and the domain goes from, let's see, it looks like -9 all the way to 7. So domain is -9 to 7, right? So I'm looking, the x value of the small point, the most left point is -9, and the x value of the most right point is +7. All right, what about the range? Well, that's looking at the y values, right? And the lowest y value looks to be about -5.5, pretty close to -5.5. And the highest value is 10, so there's my range. Now, this is why this is easy, because the inverse of a function just takes everything about x and switches it to y, and everything about y and switches it to x. So h of x being the inverse of f, basically my domain and range just switch. So the domain of my inverse was the range of the original function. So I don't have to do any work. I don't have to draw the graph. I should know that. So because the range of f of x was -5.5 to 10, that means the domain of the inverse is going to be -5.5 to 10. The domain and the range switch. And the same thing with the range. The range of h of x is the domain of the original function f of x, and that's going to be -9 to 7. So there we go. Not too bad. But again, you could go ahead and actually find these 4 points, switch the x's and y's, and make your new points for the inverse, then connect the dots, and you will see that we do have the domain and range as I just said there. All right, here's another problem. Okay, same graph as I told you. So we want here a little bit of a composition problem. So we want to take -6, plug it into f, and then take that result and plug it back into f. Okay, so kind of weird, but let's go with it. So what is f of -6? So -6 is right here. So here's -6. The output for -6 is -4. So f of -6 is -4. All right, now we're going to take -4. We're going to plug it into f. Okay, well, let's do it. So here's -4, and the output for -4 is -3. Done. There's my final answer of -3. A little bit weird, but not too bad. We're composing a function of itself. So we're just going to plug a value into the function, get an output, take that output, plug it into the function again to get my final value. All right, so here is another problem dealing with that same graph. And it says, what is the minimum value of h of x? Okay, so let's think about this for a second. H of x is the inverse. So let's look at this point right down here. So this point right down here was -9, -5.5. Well, if I do the inverse, I'm going to switch that. So that's going to be -5.5, -9. So that's going to be where? Let's see here. So -5.5 would be right about here, and then -9 is right about there. So that's going to be my new value. So what's the minimum of that? Well, the minimum is going to be -9. So basically, if you think about it, right, the minimum of the domain from the original function is now the minimum for the range of the other function, right, of the inverse. So hopefully that makes sense. So I'm just taking that low point and I'm switching it around, and I'm going to get that new point for the inverse, and that means my minimum value for the inverse is going to be -9. It was -5.5. That was for f, but when I found the inverse, it becomes the x coordinate, which was -9. So hopefully that makes sense, not too bad. All right, question number 20 here. We want to expand this logarithmic expression. So we need to know our log properties. So we know that multiplication expands with addition and division expands with subtraction. So we have log of x squared plus log of y minus log of w to the fourth. The last thing I'm going to do is use my power property, which says that these powers can fall down in front of the log. So I get 2 log x plus log y minus 4 log w. Not too bad. All right, this time we want to condense this. We have 3 terms here, all involving log base 2. We want to condense this to a single log. We want to write this as log base 2 of an expression. All right, so first here I'm going to do subtraction. Subtraction comes together with division. So we have log base 2 of x divided by k minus 3. And I guess I didn't need that extra set of parentheses there. All right, and then we still have that plus 3 log base 2 of w. All right, now note that there is no rule to separate subtraction within a log. There is no rule to separate addition or subtraction within a log, so that k minus 3 just stays there. Now we do have addition of this next log, so that's going to become multiplication, but I'm first going to move this 3 up as my exponent so I could do that. So our final answer is going to be log base 2 of x times w cubed, all divided by k minus 3. Not too bad, not the prettiest answer there, but that did take multiple logs and condense them down into a single log using our log properties. All right, here is a good exponential equation. So we have a function 3 plus 2 raised to 4x minus 1, and we want to find all such values of x such that f of x equals 35. Now, some kids actually misread this, and they plug 35 in for x. That's not what we're doing. We're not plugging in 35 in for x. We're actually turning the f of x right here into a 35. So we have 35 equals 3 plus 2 times raised to the 4x minus 1. All right, now how do I solve this by hand? No calculator. First of all, I'm going to subtract 3. So I'm going to isolate my exponential portions. So when I subtract 3, I get 32 equals 2 raised to the 4x minus 1. Now, 2 different ways I can move forward. My thinking is my x is in the exponent. How do you get rid of an x in an exponent? How do you get an x in exponent to no longer be in the exponent? Well, you use logs, right? I need to undo this base of 2. And how do you undo an exponential base of 2? You use logarithms. So I'm simply going to write this exponential statement as a logarithmic statement. So I have log base 2 of 32 equals the exponent. All logs always equal your exponent. Now, what is log base 2 of 32? That's one that you should know. 2 raised to what equals 32? That's a pretty easy one, a pretty standard one most kids should know. That is 5. 2 to the 5th is 32. So 5 equals 4x minus 1. Now I just got to solve this really easy equation. Add 1, I get 6. Divide by 4, I get 6/4, which reduces to 3/2. Nice, simple answer. But I do want to show you one other way. Go all the way back to this step right here. If you could get each side of an equation to have the same base, then the exponents must be the same. That's a one-to-one property. So in this stage, instead of using logs, I could say, well, wait a minute, the right side has a base of 2. So how about I make the left side have a base of 2, and 32 is 2 to the 5th. So I just rewrote 32 as 2 to the 5th, and now both sides have the same base. And if both sides have the same base, then the exponents must be the same, so I could get to the point where I know that 5 equals 4x minus 1, and then again I can save. So you could either use logs or you could change to the same base. But be careful because not all values can be turned into the same base, but if I'm going to give you one on a non-calculator, it's going to work out. All right, let's do a log equation now. So consider this log function, and we want to find all such values such that f of x equals 3. So once again, we want to turn the f of x into 3, and we want to solve. So I get 3 equals log of x minus 3 minus log base 2, excuse me, minus log base 2 of x plus 4. All right, so the first thing I want to do is I want to condense this down to a single log using my log properties. And subtraction of 2 logs can bring them together with division. So I have x minus 3 over x plus 4 inside of my log. Now, how do I get those x's that are inside my log. How do I get them out of my log? Like, how do I get my log to go away? Well, the inverse of a logarithm is exponential. So I'm literally just going to rewrite this logarithmic statement as an exponential statement. So 2 raised to the 3, logs always equal the exponents, my exponent is 3, equals the inside x minus 3 over x plus 4. All right, everybody should know that 2 raised to the third is 8. So I get 8 equals x minus 3 over x plus 4. Sorry, I'm running out of room here, so I'm going to move over. Now I'm going to multiply both sides by x plus 4. So the opposite of divided by x plus 4 is to multiply by x plus 4. So I get 8 times x plus 4 equals x minus 3. That's 8x plus 32 equals x minus 3. Let's subtract x from both sides. So I get 7x. Let's subtract 32 from both sides, and I get negative 35. Divide both sides by divide both sides by 7, and I get x equals negative 5. Now, one thing that typically happens, not always, but sometimes happens, you get what's called an extraneous solution. So we got an answer through the process of algebra, and we got a really good answer, really nice answer. It made a lot of sense. But if I go and plug that back in for x, something really bad happens. If I plug negative 5 in for x, I'm going to get a negative 8 right there. I'm going to get a negative 1 right here. And the problem is you cannot have negatives inside of logs. So we got an answer of negative 5, but it's an extraneous solution. This problem actually has no solutions because my function will never, ever allow x to be negative 5, because if I try to plug in negative 5, I get negatives inside of logs. And you're never, the inside of a log must be a positive value, cannot be 0 or negative. So when you're working with logs, you got to keep that in mind to always check your solutions because they might end up being extraneous. All right, because of that one being kind of difficult, let's do another one. I think it'll be really worth it. All right, so f of x equals 2 here. We want to find all such values that allow f of x equal 2. So I'm going to turn f of x into a 2, and I'm going to solve. So I get 2 equals log base 2 of x minus 2 plus log base 2 of x minus 5. All right, first thing I'm going to do is I'm going to condense this to a single log, and addition of two logs can come together as multiplication. So I get log base 2 of x minus 2 times x minus 5. And then now, how do you get rid of a log? Well, you use the exponentials, right? So I'm going to turn this log statement into an exponential statement. So I get 2 squared, base of 2, logs equal your exponents. My exponent is 2, equals the inside of that log, which is x minus 2 times x minus 5. Now I'm just going to do a little bit of multiplication. 2 squared is 4. And then I get over here, I get x squared minus 7x plus 10 when I do the multiplication. Now I got myself a good old quadratic. Hopefully you haven't forgotten how to solve a quadratic. I got to get a 0 on one side so I can factor. So if I subtract 4 from both sides, I get x squared minus 7x plus 6. And now I'm going to factor this, or I could use the quadratic formula, but factoring this is pretty quick and not too painless. So I get x times x is x squared. I get 6 and a 1, and they're both negative. That way, when I multiply them, I get the positive 6, and when I get that outside negative 1x, inside negative 6x, I get that negative 7x in the middle. So x equals 6 or x equals 1, but don't forget to check for extraneous solutions. I got 2 answers that make sense, but let's check them. If I plug in 6, 6 minus 2 is 4. That's a positive number that works. 6 minus 5 is 1. That's a positive number that works. So 6 is a good answer. But what about 1? When I plug in 1, 1 minus 2 is negative 1. Can't have a negative inside of a log. 1 minus 5 is negative 4. Can't have a negative inside of a log. So 1 is an extraneous solution. The only answer to this equation is x equals 6. All right, final question here, another log problem here. So let's go ahead and solve this log equation. All right, first thing I'm going to do on the left-hand side is I'm going to condense the subtraction of two logs with the same base can come together with division. So I get log base 9 of x plus 6 over x equals log base 9 of 2. Now I'm actually going to use what's called the one-to-one property. If I have log base 9 on the left and log base 9 on the right, then the values inside of those logs must be equal. It's the one-to-one property. So x plus 6 over x must equal 2. Now, that should make sense. I hope that makes sense. I hope you were taught that. So if, again, the property is basically this, just generically. If you have log x and you have log y, well, then x has to equal y. Because if the left side's a log and the right side's a log, then the insides have to be the same for the equation to be, well, equal. But if you don't like that, you could also go ahead and say, hey, listen, I'm going to write this logarithmic equation as an exponential equation. So I'm going to say, all right, well, not too bad here. I'm going to take my base of 9, and I'm going to raise it to logs equal an exponent. So my exponent is log base 9 of 2, and that equals x plus 6 over x. Now, again, remember what I've told you is that exponentials base 9 and logs base 9 are inverses. So essentially this exponential base 9 and this log base 9, they undo each other. Just like addition or subtraction, they undo each other, and I just get 2. So I get 2 equals x plus 6 over x. It's another way of thinking how to get to this point where I have x plus 6 divided by x equals 2. But most kids are going to go with that 1-to-1 property. Once you have a log base 9 on each side, the insides of those logs must be equal. Now, very easy to solve this. Going to multiply both sides by x. So I get x plus 6 equals 2x. Subtract 1x from each side. So I get 6 equals x. Done. Don't forget to check for extraneous solutions. If I plug in 6, I get 12. That's a good number. Plug in 6, I get a positive number as well. As long as you get a positive number when you plug it into your log, you're good to go. All right, so there's 25 questions that are hopefully going to help prepare you for a Unit 2 test for AP Precalculus.